got plus 1 there. Okay? So who's losing electrons? Sulfur's going from plus 4 to plus 6. It must be losing 2 electrons. Yeah? We okay?
Yeah.
So who's gaining electrons? Nitrogen. Nitrogen's going from plus 5 to plus 2. It's gaining 3 electrons. Yeah? We okay? Now we can use our least common multiple, lowest common denominator trick, right? If I'm going to balance the electrons lost and gained, I need to lose 6 electrons and gain 6 electrons, right? That's the least common multiple of those two numbers. Now, how many sulfurs do I need to lose 6 electrons? 3. And how many nitrogens do I need to gain 6 electrons? 2. Now that we've placed those 4 coefficients balance the electrons lost and gained, right? The others should just pop right out. That means I have 6 oxygens and 6 more. Over here I have 12 and 2 is 10. So I have 12 oxygens over here. Excuse me, I have 12 and 2 is 14. So I have, let's start again. I have 6 and 6, that's 12. 12 oxygens over here, not including the water. Over here I have 12 and 2 is 14. So I need 2 more oxygens on the left-hand side. So a 2 must go here. And if a 2 goes here, then a 4 goes there. So in other words, once you place those 4 coefficients to balance the electrons lost and gained, the other coefficients should just pop right out just to balance the electrons. And as a double check, let's check the electric charge. I've got 2 negatives here. I have 6 negatives here, but 4 positives. So the net charge on each side is -2, isn't it? How are we doing? Good? This is review as well, isn't it? Right? We did that before. All right. Let's move on to something that is at least a little bit new. Pull out the acid-base charge. Everybody got one? Yeah. I get extras. You wouldn't sit there without one because you were too, there we go, too shy to say, yeah, I can't find mine. Okay? So if you hold it so the holes are on the left, that's the acid-base chart, but we're interested in the backside of it. Oh. Yeah, I saved a little paper back there. Now, what is this list? Standard reduction potentials for half reactions. Ooh, that's a mouthful. Standard has to do with being measured under the same conditions. Okay? Reduction potentials. We'll talk about potentials later on. But these are reduction half reactions. Verify by looking at each of the reactions that reduction is taking place. Everything that's on the left-hand side of the arrow is gaining electrons to become what's on the right-hand side of the arrow. Yeah?
Yeah.
Why are they called half reactions? Can you have reduction occur without oxidation occurring? The answer is no. Reduction can't happen unless something takes electrons away from something else. And that something else gets oxidized. So we call these oxidation-reduction reactions that we're talking about in this chapter, but oxidation can't occur without reduction, and reduction can't occur without oxidation, right? Now, why are these reduction half reactions? Well, because Each of these things on the left is taking on electrons, and we've put them in order by how much they like to do that. In other words, who likes to take on electrons the best? Well, fluorine. We knew that already, didn't we? Okay? And who likes to take on electrons the least? The alkali metals, huh? Lithium, sodium, potassium. They're at the bottom there, aren't they? Now, they're not neutral metals taking on electrons, are they? They're positive ions, right? We expect metals, if they're going to take on electrons, to be positive ions. We expect metals, if they're going to lose electrons, to be neutral metals. Okay, so you verified that these are listed in order by how much they like to happen, yeah? And I'll remind you that back when we first did this, we talked about putting these elements in order by who likes electrons best, by something we call electron affinity. Yeah? And that's what we're talking about. Fluorine has a high electron affinity. Lithium, sodium, potassium has a low electron affinity. And that's just what this is saying. But there's more here, because there's more on this chart than just elements.
Does this chart cover any ones that have rules for them, or is there going to be others that we still need to look back to?
So this is not really about rules for oxidation numbers.
Okay.
That's a little different. Okay, so we're looking at reduction half reactions. I guess there must be some other table someplace that I must have to give you that have reduction half reactions on them.
No.
Why not?
It's on the other side. It's kind of like
Because the oxidation half reactions would be the backwards reactions, huh? Can we oxidize fluoride ion? Take a look at the half reaction at the very top. Can we oxidize fluoride ion? What would we do to oxidize fluoride ion? We take electrons away. And if we took electrons away from fluoride ion, what would it become? Elemental fluorine, wouldn't it? Right? So the forwards reactions are reduction half reactions. The backwards reactions are oxidation half reactions. In other words, if we're going to make a whole reaction from this table, what are we going to do? Choose two half reactions, two reduction half reactions, and turn one around, huh? And then add them together. For instance, we just did this reaction a minute ago. Yeah? Find the two half reactions that are involved here. First of all, who's being reduced?
copper.
Copper ion. Can you find the reduction half reaction for copper ion?
Yeah. No, it's right.
Yeah, it's there. Okay, so here's what it looks like. Yeah? Now we need a half reaction that involves zinc. What does it look like?
It's like zinc.
It looks very similar. It looks like this, doesn't it? But of course we need to turn that around, don't we? Yeah? Because the zinc is being oxidized. So I'm just going to swap ends here.